Hello everyone. So I'm Michael Opeti. I will share this session. We will have 5 interesting papers today. So let's start with the first one, titled Loss Contribution-Based In Situ Visualization for Neural Network Training. And the presenter will be Teng-Yok Lee.
Deep neural networks are the fundamental components of today's AI research. A deep neural network can be treated as layers of operators. Given a data item, it is computed through operators to obtain a final output. While the strength of deep neural network has been widely demonstrated, a major issue is that the training can be slow. Given a deep neural network, it should be trained first to optimize the operator's parameters, which is done by iterating through a training dataset. Nowadays, it is common to have a very deep neural networks with tens or even hundreds of layers. The dataset can be also large. A famous example is ImageNet, which has 1 million images. Also, the training process needs to iterate through the dataset multiple times. Since the training can easily take days, it will be ideal that before the time-consuming training finishes, we already can visualize what happens inside the deep neural network to detect issues as early as possible. In high-performance computing area, this is often called in situ processing. Here I quote a sentence from a survey paper, which said that in situ processing is to visualize or analyze data as it is generated. To achieve this, during the training of a deep neural network, we want to add extra code to periodically prompt the trained deep neural network. As a result, it is important that the extra code does not create too much overhead in terms of computation, I/O, and storage, so you will not slow down the training. To understand how a deep neural network works, besides the operators and parameters, it is often necessary to examine the hidden variables, which are the intermediate results within a deep neural network when processing an input data item. The hidden variables are often high-dimensional tensors, which are commonly used to visualize the deep neural network. Here we show 2 examples from previous publications. The top right shows how different parts in the hidden variables have high values when processing different images. The bottom right shows how the hidden variables change over time for time-varying data. However, it is difficult to directly apply GC visualization approaches in situ. The main reason is that hidden variables are high-dimensional tensors, which can be storage-consuming to store. It will be even more storage-consuming if we want to store for multiple data items to compare or to log them over time. Besides I/O overheads, existing visualization approaches often need to pre-process the hidden variables, which can be time-consuming. To overcome these challenges for in-situ visualization, this paper presents an efficient approach to quantitatively estimate how the hidden variables impact the training. Because the estimation is efficient in both storage and time, we can do different types of in-situ visualization and analysis, such as detecting training data that make the training difficult. We can also monitor how a deep neural network is evolving during the training. Here I will briefly review the terminologies used in the training of a deep neural network. A deep neural network can be considered as layers of operators, each of which has its parameters. To train the deep neural network, we use a batch of data items to optimize the parameters. For each data item, we do forward propagation, which essentially computes the data item through operators to obtain the final output. During forward propagation, each operator outputs its hidden variable, which will be used as the input for the next operator. When training a deep neural network, each input data item has an expected output. We will compute the difference between the expected output and the forward propagated value for each data item and the sum of differences of all data items as the training loss. Given the loss, the training process computes its derivative with respect to all parameters, so later it can apply gradient descent to update the parameters to minimize the difference. Because it is difficult to directly compute derivatives for all parameters. It is common to apply the backward propagation algorithm. To make the notation simple, for each layer, we consider concatenation of all data items' hidden variable as a long vector, such as h in the middle and O at the end in the figure below. In backward propagation, we first compute the derivative with respect to the output, which is difficultly doable. Then we apply the trend rule to compute derivative with respect to the parameters of the last layer. Similarly, with the trend rule, we can compute derivatives of the hidden variable of the previous layers, and so on. At the end of backward propagation, we have the derivative of all parameters and the hidden variables. Now I describe how the in situ algorithm models the relationship between hidden variables and the final training loss. Given an operator with hidden variable h, we denote its forward propagative value as fh. Then we consider the operator's afterward till the computation of the loss as a function called LH, where the input is a forward propagative value fh and the output is a loss L. Our goal is that for each element in the hidden variable h, called hj, we compute its weight wj, so we can approximate the function LH as a weighted sum of each forward propagative value times its weight. If this is doable, by imagining the loss as a pie chart as shown in the right, the contribution of each element hj to a loss will be its forward propagative value multiplied by its weight. To approximate the loss as a weighted sum, we apply a two-step approach. The first step is to apply Taylor expansion to the function LH and then drop higher order terms, which is commonly used to linearize a function. By using a vector of the same shape of h but with O0, which is denoted as 0h here, we can write the Taylor expansion as follows. In this case, however, we need to compute the derivative with respect to a reference point at 0h, which will be an HR computation overhead. To resolve this issue, we apply another step of approximation. As we are going to linearly approximate the function LH, it means that we are considering the loss function as hyperplane between reference 0h and the forward propagated fh, as shown in the right. Since the derivative on hyperplane is identical, we assume that the derivative at 0h and fh will be close, so here we just reuse the derivative at fh. While this is a strong assumption, it should be remembered that during the original training process, backward propagation already computes the derivative at h equal to fh. As a result, with this assumption, we can just reuse the backward propagated derivative to compute loss contribution without extra forward or backward propagation. To simplify the notation, hereafter we use bh as a backward propagated derivative at h, while fh is a forward propagated value. Then, for each element in h, its loss contribution will be its forward propagated value times the backward propagated derivative. With the element-wise loss contribution, now we can do more in situ visualization. First, remember that h is a concatenation of the hidden variables of all data items. As a result, by summing the loss contributions of elements that correspond to the same data item, we can know how much this data item contributes to the training loss. If a data item has high loss contribution, it implies that due to this data item, the loss is high. In other words, this data item makes the training difficult. Based on the data-wise loss contribution, we design a simple algorithm to detect difficult data items during the training process. When training a deep neural network, it is common to divide the dataset into multiple batches. Once all batches have been examined once, it is called an epoch. During the training, we can use a priority queue to keep the data items that contribute most to the training loss in an epoch. Once the epoch finishes, we show the selected items and then reset the priority queue for the next epoch. In the right, we show a screenshot of our in situ visualization prototype where we use TensorBoard to show the selected data items during the training. Here we show 64 difficult items after 10 epochs of training on CIFAR-10. CIFAR-10 is a dataset of small image icons, and each contains a different object. We aim to train the image classifier to classify input image icon to the corresponding object type. Among these difficult images, one seems containing 2 persons, which is enlarged here. However, CIFAR-10 does not have object classes for persons. It seems that CIFAR-10 incorrectly annotates the objects here as trucks. In such a case, it is impossible to train an image classifier to classify these as trucks. With an in-situ visualization algorithm like ours, we can detect the issue like this before the training finishes. We can also apply our approach to convolutional neural networks, which are deep neural networks with convolutional operators and commonly used when the data items are images. When using a convolutional neural network to process an image, each layer of hidden variable can be considered as multiple 2D feature maps. Each feature map has spatial coordinates, and each cell in the feature map shows the convolution result over an area in the input images. Because of this property, the feature maps provide lots of visual cues to understand how the image is processed. On the other hand, because each layer can have tens, hundreds, or even thousands of feature maps, it is impossible to examine all, and so selection or aggregation is needed. To aggregate feature maps, we utilize the important property of convolutional neural networks. Given a layer of feature maps, the same spatial coordinates in all feature maps correspond to the same area in the input image. In such a case, by aggregating the loss contribution over the same spatial coordinates, we can see how the corresponding area in the image impact the training loss. In order to efficiently aggregate for in-situ analysis, we aggregate feature maps into 2. One is called loss contribution map, which sums the positive loss contribution per location. If an area has high loss contribution, it means that this area is difficult to train. The other map is called loss reduction map, as it sums the negative loss contribution per location. If an area has negative contribution to a loss, it means that this area is helping to reduce the loss. Based on the 2 maps, we generate a view called monitoring view to monitor how the image is processed differently during the training. In earlier slides, we mentioned the selection of difficult images. In our system, once an image is selected, we will generate its monitoring view in later iterations. A monitoring view includes 2 rows of maps. The top row shows the loss contribution maps, and the bottom row shows the loss reduction maps. The columns show the maps of different layers, which are pre-specified. In each column, the top shows extra information, such as the layer name, the expected output, the computed output, and the color map of the 2 maps beneath. Our current prototype uses TensorBoard to show the monitoring view during the training, which allows users to use the slider to see the views of an image in different iterations. Here we show an example when training a handwritten digit classifier with the MNIST dataset, when one image represents digit 7 but was initially classified as digit 3. The left shows the monitoring view of an earlier iteration. In the loss contribution map of the middle column, we can see that the lower part of this digit 7, which looks like the lower half of 3, has high loss contribution. The middle shows the monitoring view of a later iteration, which still incorrectly classified this digit, but the maps started to change. For instance, in the loss reduction map of the middle column, the close in the middle started to get high value in the loss reduction map, meaning that this area was reducing the loss. At the end, this digit was correctly classified as 7. Now the close in the middle got higher value in the loss reduction map than the lower part in the loss contribution map. For in-situ algorithm, the efficiency is crucial, since it should not cause too much impact to the original process. A major strength of our algorithm is efficiency, as an element-wise multiplication of the forward propagated values and the backward propagated derivatives has more overhead. This is especially apparent for convolutional neural networks because convolution is slow. To verify this, we did a test that extended RISSAD 50 in Google's TF-SIN library with loss contribution calculation to all 50 layers. And then we tested on a batch size of 16 images of 224 by 224 pixels. Here we show a number of floating operations. We found that the floating operations was just increased by 1%. In conclusion, this paper presents the efficient algorithm to estimate how much each hidden variable in a deep neural network contributes to the training loss. Because of the efficiency, it can be utilized for in-situ visualization and analysis of a deep neural network during the training. The applications include detection of ambiguous or even mislabeled data items. It can also monitor how a convolutional neural network processes difficult images differently during the training. Thanks for listening. Any questions?
Thank you for this very interesting talk. So we are ready to open the floor for questions. You can use Discord or the YouTube channel. Well, I cannot, waiting for the first question, maybe I have one. There is a trade-off between time and accuracy in your technique because you want to go faster. So are you also decreasing the accuracy compared to state-of-the-art approach because of your approach?
Thank you for your question. But when you say accuracy here, you mean the model accuracy or the in-situ visualization accuracy?
I mean, compared to a baseline which would compute it, you try to be faster, right? So
right. Okay, so I try to rephrase my understanding of your question. I think your question is that I do lots of approximation to make the algorithm faster for in-situ. But meanwhile, it means that it's a trade-off between accuracy. So you wonder what's the impact. Yeah, but I think unfortunately, when you say accuracy here is more like, I think my approximation is not about the final model accuracy. It's more like in the middle, how I see. How accurate I model the loss contribution. And I agree, it's not an approximation. And so, yeah, so I think, anyway, I haven't done any formal calculation about the loss contribution. You will take lots of time, but I agree with you, for more solid analysis, it might be needed, yeah. Okay. And another thing, unfortunately, I never heard any algorithm can do this in situ, so I don't know.
Yeah, I understand.
But I think we can do some offline comparison, I believe. Yeah, online, I don't know
anything. You could compare on a smaller scale, maybe on a smaller scale problem, so you would be able to compare with something which run faster and do not require in situ. Maybe could be.
Right. So, for example, like I use MNIST and the CIFAR, which both are considered small nowadays. So, is there an ideal candidate to compare with other existing method, which, for example, like GradCAN is a reasonable candidate, I guess. But yeah, or maybe not algorithm. Just if we don't do this approximation, let's honestly calculate the backward propagation to the reference pointer and really compute those contribution. How much overhead or approximation introduced, I guess.
I see.
Yeah, did I answer your question?
Yeah. I see no question yet. Maybe another one, which is how people use this information. So when you observe this during training, you see that some areas are more difficult to train, some other are more easy. How the end user would use this information in your case? This
is actually a very interesting question, how to utilize this visualization. And honestly, for the second part, which is the loss contribution, loss visualization maps, I think they are interesting, but honestly, I think most now still rely on user to see, to get understanding how to really utilize it automatically, which is unknown. I personally think right now, the most useful part is the first part, which detects something potentially mislabeled. And this is actually very helpful because, like I showed, there are 2% classified as trucks. I never heard people find this. Yeah, and there's no point to train this, right? So if you realize this early enough, you can do something to stop it. Okay. Okay, thank you very much. So we have no more questions. So thank you again for your talk, and we will switch to the next one. Thank you.
So the next talk will be VATUN, Visual Analytics for Testing and Understanding Convolutional Neural Networks. And the talk will be given, I guess, by Cheonbok Park.
Hello, I'm Soyoung, today's presenter. We present VATUN, an integrated visual analytics for testing and understanding convolutional neural networks. Motivation of our work is a wide application of deep learning. In recent years, we can easily see the various deep learning applications such as image recognition, machine translation, and speech recognition. Moreover, owing to the outstanding performance of deep learning applications extends in safety-critical domains such as medical or self-driving cars. However, when the deep learning model is applied in real-world applications, there can be several weaknesses which machine learning engineers did not find before the deployment. The most popular problems are model bias and adversarial attack. In recent years, ImageNet-trained CNNs are easily biased towards texture, and adversarial attack shows that unrecognizable pattern can change the prediction results. Then, how can we prevent such issues before the deployment? The easiest evaluation measure is calculating metrics, including accuracy, precision, and recall. However, can accuracy capture the bias or adversarial attack? The answer is no. Those metrics are insufficient to find such issues. The model with high accuracy still can be trained in the wrong way or can be biased to a biased dataset. If the biased model is deployed in our real life, it will cause social and safety-critical problems. Therefore, especially in industrial circumstances, it is necessary to evaluate the trained model with diverse testing tools. We got those needs and interviewed 3 experts to design visual analytics which help users to effectively test and understand the trained CNN model. We interviewed 3 computer vision experts who are working as machine learning engineers in industries. We asked them to answer our question based on their experience. If you have a system to test a trained model before the deployment, which components do you want to include the system? Based on the answers from the experts, we build 4 requirements for our system. First, all experts consent to the need of testing data, which can be directly handled in the system, and test the model with the changed images. Experts want to manipulate images and see whether the model prediction score changes according to the augmented image. If the model predicts this image as airplane, which is correct, then will the model predict those rotated, zoomed, or occluded images correctly as the same with the original one? To answer this question, we construct these needs as a what-if scenario and build this requirement as first. Second, the experts wants to verify where the model concentrates on the given image. If the model focuses on relevant regions, like the left image, user can assume that the model is able to extract the relative feature to the classification. Otherwise, if the model is concentrated on irrelevant part, like the right image, users cannot be sure of consistency of the model when it applied in real world. To evaluate whether the model classifies an input image with relevant evidence or not, our system should visualize evidential parts of the input image. Third, some experts want to understand the reasoning procedures of the model from a given input. For example, if a car image is an input, the model can learn the car starting from the red, hill, and finally the car. This requirement focuses on understanding the inner working process of model, while requirement 2 is concentrated on testing a single image. Fourth, we aim to combine all validation steps as multi-aspects and make them sync. For instance, a popular example of the blinded man and the elephant, we usually find it hard to understand and convince the whole contents when only a single standpoint is given. Likewise, it is time-consuming and inefficient to find a new bias or error via a single testing view. Therefore, we build our last requirement to let users analyze the problem with diverse aspects. Based on the previous 4 requirements, we design our visual analytics tool, VATUN. VATUN, visual analytics for testing and understanding the convolutional neural networks, consists of 4 views. First is data embedding view. Second is testing view. Third is network view. 4 is simulation view. For sure, each network interacts with each other. First, the data embedding view. In here, we aim to help users to access the corner case data instances easily. As you can see, we can easily observe the distinct instances which have different colors with neighboring ones. Also, user can approach their interesting image by zooming the view. If a user zooms in the data closely, our view transforms its dot as its corresponding image. Second is testing view. In testing view, we aim to provide a what-if scenario experience to users. If user generates augmented image by changing conditions or making a mask on the image, the user can watch how the prediction score changes according to the what-if condition. In addition, we provide augmented results, which summarizes how the prediction score changes according to the extent of condition variations. Also, via the GradCam results of each origin and augmented image, the user can check whether the model classifies the image based on the reasonable basis or not. Based on the GradCam, user can mask the highly relevant part for the prediction label and observe that the prediction class changes from dog to bird. Third is network with neural pattern recommendation. Our system provides not only the data instance view, but also the network view. As the first section of this view, we simplify the network view as the unit visualization to introduce the size and scalability of the model. Along with the neural network view, our system introduces a novel network understanding method, neural pattern recommendation. For the sake of time, we will intuitively explain the neural pattern with our toy example. Let image x1 is input, and x1 have the highest activation value at first, and second node for its layer. We make a node sequence for x1, which consists of 1, 1, 2, and do the same process with the other examples. After getting node sequences for all datasets, we compare its node sequence in a subsequence level. If one or multiple subsequences appear frequently in diverse images, we group the whole node sequences and their corresponding image X, and we define this group as neural pattern. In practice, we consider both convolutional and fully connected layer and make the minimum size as 4 for the length of subsequence and the number of images to span a neural pattern. These are examples of our neural pattern results in CIPR10 dataset. We pre-compute all neural patterns for the dataset, so the computation time is not required at inference. Based on the neural patterns, our system recommends neural patterns which include an image instance or filters the user selects in another view. For instance, if a user clicks a bird in the sky in the 2D embedding view, the user can observe two apparent neural patterns. First is pattern with sky, which consists of diverse classes, while the second one includes bird class only. Lastly, the simulation view. We aim to help users to overview the robustness of the model at class level according to the extent of image variations. In this image, each column is class, and rows are the augmentation conditions, including blur or rotations. This view can be explained as the summarized view of model testing. For example, we can see the distant difference between the airplane and horse. While the airplane is robust to the rotation, the horse is very weak to the rotation condition. This can be explained that the dataset of airplane class consists of diverse directions, while the horse class consists of horses heading only left or right. To show efficiency of our integrated view, we constructed a user study and developed a user scenario based on it. We aim to build an integrated system which provides efficiency to users via the complementary relationship between each view. For instance, in the 2D embedding view, a user found a cat image predicted as deer and embedded in the deer class instances. The user clicked the image and saw the breadcrumb results, but the testing view did not fully explain the misclassification. Therefore, the user goes to the neural network view to get help. Along with pattern 4 and 5, the major character of images is that the grass appears as the background. As a result, the user can resolve the ambiguity from the testing view and conclude that the model is biased to grass when classifying the deer class. To this end, we introduced VATUN, an integrated visual analytics system which provides both testing data and understanding network approaches. For our future work, we plan to extend the study with such safety-critical dataset or circumstances. Thank you for the listening, and you can join our demo in http://vatun.kr.
Thank you very much for this interesting talk. So we are ready to open the floor for questions. So I don't see yet any questions. So remember, you can use Discord or YouTube channel. I have a question on when you have this layer. So I think it's R3 requirement. You have different layers, and you say you can recognize grass, or for the cars, you have the cars, and you have another layer which corresponds to higher level patterns, right? But my question is, in the model itself, how are these layers identified? Are they someone give a label, right? You have to give a label for these different layers. Is my question.
Did you mean the higher level of our model, or? Yeah,
and each you have the layers in the models, right? And there are some semantic associated to the layer. Usually, the closer the layer to the input, the more fine-grained and global features. How they are defined in your case? Because if the user say, "I want to see birds in the sky," you have this example where you have the sky, the image with blue sky, and then you have image with bird in a blue sky, right?
Yes.
How do you identify this text-based search? Is it by image search, or is it by text? Do you have some
is it
label
in
to the
image?
layers?
Image.
So the user will query by image. He will spot, for instance, the bird, and it will automatically give all the layer which contain the bird identified in that layer.
I think you're asking about our neural pattern recommendation.
Yeah.
Yeah, and when user click the dot on the data embedding view, and we can see on the image on the testing view, and as you said, the user only see the picture and the related neural patterns, just like our examples, like skies with bird, or car, or ships. So it's not given. Our model doesn't consider the text or something other.
So you assume all the
yes.
If the birds are extracted in one layer, all the birds will be in one layer. But it could happen that maybe in previous layer or after layer, the birds, some birds appear also, right? The isolated pattern of the bird. It's not predefined, it's learned. So it could happen that
when we have a pre-trained model on CPR10, if we select a node in the layer, then actually our all of the neural patterns which occur in three successive layers, like 2, 3, 4, and have the highest activation score on the 15, 13, 50 on each layer 3, layer 4, layer 5. Then we will we actually pre-calculate all of the neural patterns, and we have them. And if user select a node select a node like the layer 4, 15 node, then we will just pick up the pre-calculated clusters, and which have the same node the user selected.
So that's the user who, with the eye, spot what are meaningful patterns, and by selecting them, it happens that in that layer or in the neighboring layers, similar patterns are encoded. Okay, I think I got the point. Okay, I don't see other question. Maybe we maybe have to switch to the next talk if nobody has any question. Okay, so thank you again for your presentation.
Thank you.
So let's go to the next talk, RoomCanvas, a visualization technique for spatiotemporal temperature data in smart homes. Presentation will be given by Bastian Koenig.
Hello everyone, my name is Bastian Koenig and I'm with the Computer Graphics Systems Group here at the Hasso-Plattner Institute in Potsdam. Together with Daniel Limberger, Jan Klimke, Benjamin Hagedorn and Jürgen Döllner, I developed a system for the visualization of spatiotemporal sensor data in the context of smart homes. The system is called RoomCanvas and I'm very happy to be able to present it to you today at EuroVis 2021. The motivation for our work stems from the increasing availability of low-cost IoT-enabled sensors in living scenarios or buildings. The sensor data collected by those sensors is usually sent to cloud services that promise to deliver some value to their customers or users, but often the data is not accessible in tools that allow users to explore the data, to monitor it, to visualize it how they want it. Existing systems offer mostly text-based representations of the current sensor values, or they are tightly coupled or integrated into expert software such as computer-aided design or CAD software. That's why we thought that there is a need to develop systems that allow users to explore, monitor, and understand spatiotemporal sensor data within their own homes or buildings that is available not only to experts, but also for non-experts. That's why we designed and implemented a web-based interactive visualization system called RoomCanvas that allows users to do exactly that, to visualize sensor data from their respective homes collected by small IoT-enabled sensors. I'm now going to show you a quick demo of the system. You can also visit roomcanvas.dev to see a live demo for yourself. When users open the visualization, they are presented with a 3D representation of their respective home or building. Right next to the building, they can see that there is some date and time selected. And if I now enable the visualization of the sensor values, I can see that by default, per room aggregated sensor data is shown for the respective time. I can change the time and date and see how the aggregated values change over time. But this interpolation is quite coarse. It's only giving us the values per room, which might be interesting in some senses. But it would be more interesting to see how the values are actually distributed within the individual rooms. And that's why we can also enable spatial interpolation. How the spatial interpolation works is what I'm going to explain you after this live demo. But what it does is that it's showing for each position on the surfaces, so on walls, floors, and ceilings, the interpolated sensor values for this respective position based on the sensors installed in the apartment and the actual distances to those sensors. So it's taking into account any boundaries or any obstructions by doors or walls and windows and other geometry within the scene. So it's a boundary-aware volumetric interpolation that you can see in action here. Combined with the temporal interpolation, we can see that the visualization allows to quite easily identify different clusters of an increased or decreased temperature within the apartment throughout the day. The simulation of date and time is supported by real-time shadow mapping that shows shadows cast by the approximated sun position at the respective time and date. We can also enable some labels to show us the sensor values at the currently selected time and date. So if we change the time now, we see the labels representing the respective values of those sensors. Notice how the values presented change their respective position. This is due to an automatic label placement algorithm that I will also talk into detail a bit more on later on. In addition to the surface visualization, I can also enable a volume-based rendering that really shows the potential of the volumetric data interpolation that we have implemented. You can see how through, for instance, the walls here on the left side of the screen, facing outwards of the apartment, so with the windows that face to the outside, to the streets, that the outside temperature influences the internal temperature quite a lot. And this is especially clearly visible within the volume rendering that we have implemented, because you can easily see vertical differences in the interpolated values for each position in the rooms. Together with interaction events, such as highlighting of the respective currently hovered over rooms, this can easily lead to multiple linked view scenarios, for instance, where users can further on interact with the 3D representation of their respective homes. After I now have showed you a quick demo of the system, I'm going to talk about a few details regarding the system design and implementation. The system itself consists out of a few server-side pre-processing steps that you can see on the left side of this slide, and also the web-based visualization system that I've just shown right in the demo. What the pre-processing does is it takes a floor plan, creates a simplified 3D representation out of it, accumulates certain geometric details into basically semantic information about the rooms, pre-computes global illumination effects such as ambient occlusion, adds a context geometry, so what you just saw in the visualization, basically the base volume indicating the floors below the currently viewed apartment, and also certain information is pre-computed regarding the sensors. And this is what I want to talk about in detail. One thing that is being pre-computed is so-called sensor distance maps or sensor volumes. So for each of the sensors, we have to know for every position in the apartment or in the actually in 3D space, how far this respective position is from the respective sensor. But since this also has to be taking boundaries into account, because we do not want to have very thick walls, basically letting sensor values drip through them, we have to take the spatial structure of the building into account, and this is what I'm going to talk on later on. Another thing that I'm going to explain is the automatic label placement algorithm that you've also just seen in action. So as I just explained, we need to know for each position in the apartment how far the position is from the respective sensor. For this, we pre-compute the so-called distance maps or distance volumes for each of the sensors. We do this by creating a voxelized cuboid that spans basically the whole apartment or building model. Within this cuboid, we then flag any voxel that intersects with any kind of polygon, so with the wall or with the floors or with the ceilings. And this allows us then to apply a modified flood fill algorithm that takes those boundaries into account. So starting at the respective sensor position, we basically fill the 3D volume with values where we basically keep track of the distance to this respective position. And note that this flood fill, as you can see here, basically takes the obstructions into account. So it's not going right through the wall, but instead it has to take the path through the door. So the resulting representation within the 3D volume keeps track of the actual distance, taking boundaries into account at each of the volumes voxels. The result is then this 3D representation of interpolated distances to the respective sensor. And in order to be able to work with this in the real-time web-based 3D visualization, we have to basically encode this into a 3D texture format. For this, we split the lower and upper 8 bits into one respective PNG image each, allowing us to manually inspect and easily debug the respective sensor values by having a representation that you can easily see, like the upper 8 bits, and still have basically the quality enhancement caused by not only having 8 bits, but 16 bits instead, caused by the lower 8 bits encoded in the images that you can see on the right side of the respective figures. The second topic that I want to talk about is the labeling algorithm that you've also just seen in action. What this algorithm does is it's taking label candidate positions, which are currently manually pre-created, but could easily be pre-computed during the pre-processing steps as well. For each of the candidate positions, the algorithm takes into account their respective anchor point, an upwards facing vector, a running direction vector, the cross product of basically the upwards and running direction vector, so the forward facing or normal vector, and also a maximum available length. And all those things are taken into account at each of the rendered frames on the CPU side. So for each frame, we basically find out the currently best positions to place labels for the respective sensors. And since the corresponding computations can be a bit more expensive, one could be more expensive than the other one, we basically decided to put them into order, ascendingly regarding their computational complexity. So we start with filtering out as many labels as possible using computationally quite cheap comparison or filtering, and then only if candidate positions basically go through this process and have not been filtered out yet, we continue with the computationally more expensive comparisons or filtering conditions. So the first filtering rule that the algorithm uses is what is also visualized here on this slide. It's basically checking whether the label faces the camera or faces away from it. So what we do to calculate this is we take the forward-facing normal vector, which is indicated with the blue arrow in the visualization, and basically just look at the dot product between this vector and the vector that goes from the camera position or camera eye to the respective label candidate's anchor position. We can then filter out every label that does not face the camera. And what we do next is that we filter out every label that is not inside the viewport. To do this, we transform the anchor point of the respective labels or label candidate positions into normalized device coordinates, or NDC, and basically just check whether they are inside or outside the value range of -1 to +1 on the X and Y axis. And if they are not, we assume that they are outside the viewport, and thus we filter them out. The third step is to check whether the labels are facing upside down, so basically whether they are going from right to left, because we only want to have labels going from left to right in this left to right representation that is rendered here. We do this by, again, transforming to normalized device coordinates, but this time we transform the upwards facing vector B, so the one indicated with the green arrow, and basically check whether it's going up or down in screen space. And the fourth step is a bit computationally more expensive, and that's why we, as I explained, put it down in the order of those filtering rules so that it only has to be executed for labels that have passed all the previous filtering rules. What we do is we check whether the label would be obstructed by any geometry, so if there would be anything in front of it. We do this by having a readback pass that reads back depth values from the GPU and allows us to compare the actual visible most camera-facing position at the respective screen position, compare this one with the world coordinate of the expected label position. And if it's not the same, then we assume that there is something lying before the visualization, or like before the label, and it's obstructed by something, so we filter it out as well. If multiple labeling candidates pass all those filtering rules, then they are compared using a metric-driven comparison, which basically, as I said, takes into account, for instance, their length and compares them and prefers labels that have more length available for their display. Regarding follow-up work, we see quite a lot of interesting areas that our work could be extended to, or that it could be applied to. One thing is that it could be easily extended to larger buildings and industry facilities, leading to very interesting use cases, especially when taking not only temperature data, but also other sensor data into account. The second thing is that the placement of the sensors and their distances to each other could actually be optimized. So you could think of a system that allows users to find out basically the best position to place sensors within their respective home or apartment, resulting in a better volumetric interpolation. And third, the process of the manual floor plan creation could, of course, be simplified even more, or simplified at all. For instance, by offering a LiDAR-based point cloud capture system that preprocesses data and produces a simplified 3D floor plan representation, similar to the one that we've just showed in the sample visualization. Providing additional context, for instance, via a simplified 3D city model, could also be very interesting, because it would allow users to potentially get a better understanding of the actual surroundings, influencing some of the sensor values maybe even. We are really looking forward to getting feedback from you. We would be happy to work together with you on projects that you have in mind regarding the visualization of sensor data in such systems as we've just presented. Note that the prototype that I've shown is publicly available and is and will be further developed at roomcanvas.dev. And you can also go to source.roomcanvas.dev to get the toolkit for the server-side preprocessing steps that I've just described. Here are the sources for our presentation. And we are really looking forward to your feedback and your questions.
Thank you for the interesting talk. So we have one question from Teng-Yok. I have a non-research question. Does your system allow users to walk into the room, or are users only allowed to see outside the room?
Yeah, very good question indeed. I can show you a quick example actually of how this is indeed possible. We have another building model here on the screen, and if I just zoom into the scene and move the camera into the building, then you can see that it's indeed possible to view the insides of the respective rooms. I have the interaction turned on here, the highlighting, thus we have those stripes displayed there. Don't get drawn away by them, but yeah, as you can see, you can move into the scene, and all the interpolation and volume rendering especially are designed in a way that they, for instance, by using backface rendering, in the end allow for showing all of the interpolated sensor values also from inside the building.
Okay, thank you. We have time for our last question from John Sommer. Is there an easy way to import own 3D buildings? For instance, can you just import Blender models via OBJ format?
Very good question as well. Let me also quickly switch back to the screen share here. Indeed, you can do that. So the examples that I've shown in the presentation were actually created in Blender and then imported as a GLTF standard file. So it's conforming to the specification. In the end, it's a binary GLTF file that was loaded there. So this is exported right away from Blender. And what you can see on the screen right now is what we've also been working on. Basically, it's an import script or import process for importing models from, you can see on the left side of the screen, Sweet Home 3D. So software that allows you to easily model your own home or apartment in 3D. And this was imported in RoomCanvas in the visualization on the right side as well. And as you can see, the style is similar to the one that I've shown in the presentation. So it's not showing any furniture. Instead, it's only showing a very clean and basically minimal visualization of the building. And you can, as you see, easily import existing models created from other software into the system.
Okay, thank you very much. Thank you again for the very nice presentation. Please feel free to continue the discussion on Discord on Topia channel, and let's us thank again our speaker. So now we will have the talk SailVis Reconstruction and Multifaceted Visualization of Sail Shape by Danfeng Mu.
Danfeng. Today I'm going to present you SailVis, Reconstruction and Multifaceted Visualization of Sail Shape. The main driving force of a sailboat is its sail. When set to an appropriate sail shape, it generates a lift force that makes the boat advance. However, different wind and sea conditions imply different settings to make the boat go faster. Small difference in the sail shape may result in winning or losing a regatta. Hence, it is of high interest to find out the optimal relation between the sail shape and weather conditions. According to the weather conditions, to control the shape of sail, sailors tighten or loosen ropes attached to different parts of the sail. This process is called trimming. In this video, we can see how a sail is trimmed by pulling a rope. We can see that the sail gets flatter and tighter. Nowadays, sailors rely on their naked eyes to check the sail shape. Mastering this visual inspection requires years of experience. Independent of sailors' experience, visual inspection has limited accuracy. Moreover, due to the wind changes, the sailor might need to adjust the sail shape frequently, making it hard to memorize the shape at different time instants. As a result, it becomes difficult for sailors to communicate the shape to other sailors or coaches, as well as to compare sail shape under similar wind conditions in order to find out the optimal training and consequently improve performance. To address the issues of visual inspection of sail shape, researches have been conducted to measure and analyze sail shape. There are two main trends of these researches. The first one is use dynamometer to measure the pressure distribution across the sail while measuring the sail shape. To use the dynamometer provides the accurate but sparse reconstruction as shown in the image of the reconstructed sail model from DYNA dynamometer boat. The other trend is based on photogeometry by detailing visual cues with high contrast, like sail stripes, to retrieve the curvature along these stripes, or by attaching pasty markers on the sail cloth to retrieve a complete sail shape. Methods that rely on the sparse point cloud generated with the dynamometer do not allow to explore the details of the sail. On the other hand, while photogeometry methods can achieve denser acquisitions, the resulting data has not been used to support sailors in improving their decision making. In order to fill the gaps of the existing research in cell shape and sailing performance analysis, we developed SailVis, a multifaceted cell shape visualization aiming to support sailors investigate the optimum cell shape of certain weather conditions and enhance their training process. Our main contribution lies in the development of an interpretable pipeline to reconstruct the cell shape from the sensor point cloud data, and the visualization pipeline to inspect cell shape data at different levels. The first level is a hierarchical visual inspection of a cell reconstruction. The second level is a contextualized comparison approach to contrast cell shape at different time intervals. The last level is a contextualization pipeline to compare cell shape with speed performance. SailVis is illiteratively designed in close collaboration with a domain expert from the Sailing Innovation Center in Den Haag. He has 4 years of experience working with technological projects in the sailing. The end product of our visualization tool would be the sailing coaches. Our presentation consists of 3 parts: the acquisition of the cell shape and sailing performance data, the reconstruction of the cell shape, and the final visualization. Next, I will introduce the data acquisition process. The data acquisition starts by attaching coded markers on the cell. Based on photogeometry, 2 photos of the cell shape are taken from different orientations at the same time. These coded markers are then identified, and their position can be calculated from the photogeometry methods. Video clip from our data acquisition process. We are on the coach boat that was sailing parallel to the training boat. We can see that the coded markers are attached evenly on the cell clothes. The photos of the cell shape are taken at the frequencies of every 2 seconds. The sailing performance data in our study is defined as the boat speed that are acquired by the GPS tracker attached to the boat. Now that we come to the second part of our study, the reconstruction of cell shape. The first step of the reconstruction is the triangulation of the cell shape point cloud. A 3D cell shape mesh is generated after the initial Delaunay triangulation and PN triangle remesh algorithm. Due to the sun reflections on the cell or the occlusion of the sailors, the acquired cell shape point cloud might be incomplete. As shown here, the right part is mostly missing. In order to complete the missing part, a template cell shape is deformed under the constraint of the incomplete point cloud to give an estimation of the complete cell shape using Laplacian survey editing. In order to extract more accurate features of the cell shape, the cross-section of the cell is extracted by the intersection of a horizontal plane with the cell mesh, generating a set of points on the plane. We then fit a polynomial curve on these points to extract the cell section and compute the cell shape features. To simplify and get a detailed view, we extract these characteristics from the cell shape based on the interviews with the sailing experts. Among them, the camber is one of the most important characteristics, which is the maximum distance from the cell close to the chord line. We come to the last part of our study, the visualization design of SailVis. Now that we have the reconstructed cell shape and the extracted cell shape characteristics at the cross sections of every 1% height of the cell shape, we need to use them to support sailors find out the optimum cell shape given a certain sailing condition. Towards this goal, we need to design an effective visualization dashboard to enable sailors to inspect and analyze the cell shape, as well as to compare them to find out the relation between the cell shape and sailing performance. In order to fulfill the visualization task, we designed the SailVis dashboard. It consists of the following 4 parts. On the left is the sailing context, which includes the speed light chart, the real image of the cell, and the boat track of the training run. They can also be served as a selection tool. In the middle is the 3D cell shape, which gives an overview of the 3D structure of the cell. Beside it is the characteristic heat map, gives an overview of the characteristics of cell shape along the cell. Inyoup is a profile visualization, which enables sailors to view the cell shape in their familiar way. Next, I'm going to introduce each visualization component separately and end it with a demo. First is the 3D cell shape visualization design. It is important to understand the spatial distribution of the camber on the cell, as it gives important clues if a training is appropriate. So we color-code each mesh vertex according to its camber value to provide this spatial distribution. In addition, it enables sailors to view the camber in a direct and intuitive way. In order to better perceive the different camber regions, we draw contour lines on the color-coded cell shape. It enables the comparison of cambers in terms of area between different cell shapes. For the rendering of the 3D cell shape, we use a shader to interpolate camber value for each pixel from vertex of the cell shape mesh, and color it accordingly to the color map directly. Then we use white ambient light to avoid the uneven light reflection on the cell that could possibly influence the camber color. The next one is the characteristic visualization. From the 3D cell shape visualization, we can have an overview of the camber on the cell. However, there are different characteristics of the cell shape that are very important. Here is a table of these characteristic data on the cell cross-sections at the position from 10% to 90% of the cell height. In order for sailors to get an overview of this cell shape and find their interesting areas, we present the characteristic heat map, where each column represents a variable and each row represents the different height of the cell. Each position is color-coded according to the variable it represents and its quantitative value at the height. By inspecting the 3D cell shape and characteristic heat map, sailors can get a general overview, but they cannot link the shape and the characteristic together. One way to present a more precise shape of the 3D cell shape, and also one commonly used in the sailing domain, is to visualize a cross-section of the cell, in other words, the cell profile. The goal of this profile visualization is to help sailors inspect the cell shape in more detail and identify the relevant features of the cell. This is carried out by showing the result of the intersection of the mesh and a horizontal plane at a given height. Next, I'm going to show the demo of our SailVis dashboard. On the left, there's a chart of the sailboat during the whole training, each red dot indicating that at this position the sail shape is available. Sailor can click it to see the speed and time of this position, and also double-click it to choose the current sail shape. Above it is the speed light chart. The sailor can see the corresponding speed at this point. It can also serve as a selection tool. Beside it is the real image of the cell that was captured during the data acquisition, so the sailor can get more indication of the sailing context. And here is the 3D cell shape. Sailor can examine it by rotating it or zooming and zoom out. And here is the characteristic light chart with a tooltip indicating the characteristic and its corresponding value. And sailor can also transfer color map of this 3D cell shape to this one that's corresponding to the maximum camber in the characteristic. And below there's a table of the characteristic data that corresponding to 50% height of the profile. And the curve of it can be seen from the profile visualization. Sailor can also choose to see the profile at different heights by using this height slider, while this blue line indicating the position of this profile. The smoothness of this curve can be adjusted by this curve fitting parameter. to make it more smooth or more close to the intersected points with the mesh, so that it's possible for sailors to see the wrinkles on the sail clothes. If the sail shade is incomplete, shown here because of the sun refraction and the occlusion of the sailor, the left part of the sail is missing. Sailors can choose to see the default template of using this incomplete point cloud as input. That complete this missing part and can also use as an explanation of the complete sail shape. For the comparison, sailors can choose to see how the sail shape varies with the same configuration. As shown here, the sail shape on the right side has a more stretched vertically inner contour area, which means the extension of the mean driving force. For the comparison of the characteristics, we can look at the heat map, and we can see that the right one, the entry angle and the twist angle is in general largest on the left one. For the comparison of their profiles, we overlap the profiles to see the small variation of them. And this can also be adjusted by using the height slider to see the comparison of the profiles at different positions, or to see them individually and compare them. Now let's get back to the presentation. For the case study, the participants are two setting experts involved in the visualization design, and they evaluate the dashboard by interacting with it and answer questions regarding the quality and usability. Here is their feedback. The reconstructed sail shape will match their expectation, judging from the real image of the sail, and the deformation model are reliable when it comes to the missing points. The characteristic heat map can help them to summarize the sail shape better, but a higher resolution will be needed for a better usability. In conclusion, they are able to extract and communicate about preliminary training hypothesis of sail shape and sailing performance. However, for stronger analysis and validation, other information is needed, like the wind condition, sea state, and training information. In conclusion, we present a visualization framework for visualizing the sail shape and sailing performance. It provides insights into the optimal sail shape, but the causal relation between sail shape and sailing performance cannot be guaranteed yet due to missing the weather conditions. It is considered as a pioneer towards a more comprehensive sail shape visual analysis system. For the future work, there are several directions we can go. One of them is to improve the reconstruction process and reduce the number of barcodes by constructing a sail shape physics model. In addition, we could also acquire other relevant information of the training, like the wind conditions, sea state, and training information. If we want to achieve a stronger linkage to the sailing performance, an average sail shape can be implemented during a certain time interval to reduce the influence of high-frequency change. At the end, I would like to mention that this research is embedded in the project called VATUN, funded by European Union. It was done in collaboration with the following research partner: the Sailing Innovation Center at Geo Delta. Thank you for your listening.
Okay, thank you very much for this interesting talk. So let's see if there are some questions. Cannot see question now. So I have one. When you have this curve fitting part of your interface where you can change the order of the curve to fit the data, the observation, right? I wonder, do you take into account the uncertainty in the measurement? So when you, from the start, you take a picture of the sail, and you get some depth measurement, but this depth is probably there is some error or uncertainty in this measurement. So do you take that into account also for your curve fitting model in the interface?
Yes, the measurement accuracy of the point cloud is like 1 to 1.5 centimeter. And we also take that into account. That's why we implement this parameter fitting algorithm for the curve fitting. So like the user can actually adjust the curve like to within this like measurement error, and to see like what would be like a better expectation of the curve judging from the photo.
Okay, but you do not display this error bar on the curve fitting interface, right? Because it could help the user to say, okay, here I have a small error bar, so I should fit well. In this part, there is a bigger error, so I can afford more smoothness, for instance.
Yes, but actually, like each point, they have like the measurement accuracy is the same for each point, so we cannot tell like which point has like higher accuracy than the other one. So we can only have like a more general
it's more global
parameter. Yes.
Okay, thank you very much. So I think we have to switch. I don't see another question, so please feel free to continue the discussion on Discord, and we will switch to the next presentation. Thank you again for your presentation.
Thank you.
So now let's have the last talk of this session, RISSAD, rule-based interactive semi-supervised anomaly detection. The presentation will be given by Jiao Teng.
Hello, I'm Jaegul Teng. We're presenting our work, RISSAD, rule-based interactive semi-supervised anomaly detection. This work is done by me and my advisor Eli Brown from DePaul University. Anomaly detection is currently an active area of research. Unusual data points are sometimes the most important ones to investigate, but discovering them is difficult due to multiple challenges. What constitutes an anomaly for a given context is often poorly defined, and anomalies are unusual by definition. So getting sufficient labels to train models to find them requires special attention. Researchers have contributed various techniques to deal with those challenges in the past few years. For example, FluxFlow contributed a timeline visualization tool to analyze anomalies to user behaviors in social media platforms. It combines a scatter plot-based visualization and a sequential model to identify malicious behaviors on social media platforms. It uses the one-class conditional random fields algorithm for anomaly detection. RCLens built a view system to identify rare categories based on active learning. It incorporates a heat map-based visualization for feature selection, and a local outlier factor-based algorithm is used for anomaly detection. CloudDAT introduced a view system that detects anomalies in cloud computing systems. It combines a heat map-based visualization with sequential visualization that adopts a novel unsupervised learning technique for anomaly detection. EnsembleLens presents a hybrid approach that ensembles multiple state-of-the-art anomaly detection algorithms and assists the users in interacting with data. The tool also allows the user to learn weights for each unsupervised technique. Past work has contributed many useful visualization techniques to guide the users in detecting anomalies. However, these require the user to engage with anomaly detection algorithm or technical concepts directly. They also do not provide a way to interpret the anomaly patterns in clear and descriptive words that are easy to understand even for the non-expert users. Inspired by this, we developed a technique that enables the users not only to identify and predict anomalous points, but also illustrate these anomalies in clear and descriptive rules. It also provides a mechanism to differentiate anomalies of different types based on a semi-supervised model, which does not rely on a fully labeled dataset. Before we talk about the exact workflow of the whole system and its visualization aids, I want to briefly talk about the main parts of the algorithm. The algorithm is called ADOA, and it is first proposed by John Axel from Nanjing University and Ant Financial Group of Alibaba in 2008. We modified the algorithm that incorporates human interactions. The algorithm is based on the assumption that anomalies distinct from the normal points while close to other anomalies in distinct clusters. Given this assumption, the algorithm first uses k-means to cluster labeled anomalous points into different clusters. The cluster size is a manual input, and each cluster of anomaly represents different types of anomalies. Once the anomalies are clusters, similarity and isolation scores are computed. Isolation score measures the similarity of unlabeled point. The isolation score measures the isolation of one unlabeled point to the majority of normal points, while the similarity score measures how similar that unlabeled point to each anomaly type. After that, a user may choose to assign the unlabeled points to one of the cluster. The system will auto-label the others based on a combination of those two scores. Finally, a classification model is run on this labeled dataset for prediction. As mentioned previously, after the auto-labeling of all unlabeled points, the data is then fed into a classification algorithm. The original ADOA uses SVM. However, since the algorithm does not produce any descriptive rules, we decide to use decision tree as the classification algorithm. We have run simulations to ensure that this modification will not result in much sacrifice in accuracy over a different number of user interactions. Here, we use AUC as the accuracy measure. We also compared it to two other algorithms, a decision tree that is run only on the labeled samples of our dataset, and the isolation forest, which is a state-of-the-art algorithm since they represent a fully supervised approach and an unsupervised approach. The simulation results are shown on the right. As we see, for all four datasets, our modification, which is ADOA tree, has similar performance as the original algorithm ADOA SVM. As for the other two, the ADOA tree outperforms the decision tree under all situations, and it outperforms the isolation forests in most cases given sufficient number of interactions. The advantage we get from the modification is that now we can produce the rules. We break down the modified ADOA into pieces so we can incorporate user feedback and view aids. Here's the total workflow of the system. At the beginning, all points are assumed to be normal cases. The isolation scores are computed. Using the visualization that builds on isolation scores, user can label some anomalous points before the first step of ADOA in which they are clustered. The number of clusters is chosen by the user to reflect how many types of anomalies they want to see. Then the similarity scores are computed for each point to add to each anomaly cluster. Based on this information, the user can label more points and the system can auto-label the rest of the points. At last, they are fed into a rule-based learner like the same tree to output rules. After that, the user can further refine the rules by labeling more points or overriding the previous ones by checking the learned rules. This creates a feedback loop for the user to constantly refine the rules as they deem necessary. As we noticed, the modified algorithm requires some human interactions. In order to make them work better for human understanding, we incorporate visualizations to help users to label and understand rules. The tool is coupled with 5 different components, and we will go over it one by one. The first one is the scatter plot, generated using multi-dimensional scaling from the original features. The reason why we use MDS is because it's straightforward and no parameters that could cause misleading groups that would distort the perception of outliers. And this shows the overall layout of the points. It can also help users to identify the number of clusters for anomalies. It is connected with a table view, so when the mouse is over a point, the associated row will be highlighted in green and put to the top of the table. The barcode plot is a visualization technique to illustrate the distribution of data by attribute. Each column represents an attribute. Each thin line inside the column represents a data point. The barcode plot is linked with scatter plot. When a user hovers over a point in scatter plot, its associated lines in the barcode plot are highlighted in gold color, as shown on the bottom. When a user hovers over each line on the barcode plot, the percentage of the associated data point with its attribute name is displayed at the bottom, as shown on the top. The barcode plot allows the user to bring their knowledge to the task, meaning if they know what attributes are most important, they can directly refer to those. The violin plot is used to show the distribution of isolation and similarity scores of all data points. As shown on the left, the first plot is for isolation score, and the rest are similarity score for each anomaly cluster. When users hover over a point in scatter plot, its relevant position in the violin plot are highlighted in black lines, as shown on the right. This helps the user to decide how to label a point. Once the user believes they have labeled enough points, and they can click the Generate Rules button on the top of the right corner of the rule panel, as shown on the left. The user can also switch between rules describing different types of anomalies and the normal class by selecting the rule type drop-down menu on the top right corner. Next to each rule, there's a highlight button. Once clicked, the associated points in a scatter plot are highlighted in black circles, and the associated lines in barcode plot will also be highlighted in gold color. Next, we will demonstrate with the usage scenario. Imagine a professional winemaker wants to find out wines with anomalous characters. He knows there are different types of anomalies, given the diversity in wines, but not sure exactly how many. He already collects the wine data and selects the ones with high quality and who wants to summarize the patterns of anomalies in descriptive rules. In this case, our prototype offers the help to him. Next, I will go over it step by step. This is the initial state of our prototype. We start with all points assumed to be normal and marked in blue color. The user first searches for points that are distant from the center of the population. And check their isolation scores. Then we selected the ones with higher isolation scores. In our case, we select the points with scores higher than 0.6. Now we end up with 3 points where 2 points are closer to each other, and the other one is standalone. So we assume the size of anomaly cluster is 2. We put 2 as the cluster size and hit the submit button. The system will automatically compute the similarity scores and update the violin plot. Since now we have similarity scores for each anomaly displayed in the violin plot, we can then select the points next to the already labeled anomaly points in the last round with a similarity score higher than 0.6 to the nearest anomaly cluster. After this step, we can click the Generate Rules button, and the rules would be displayed at the rule panel. We can highlight the predicted points associated with each rule by clicking the highlight button. For example, this is a rule for normal case, and the selected points are displayed on the scatter plot. This is a rule for anomaly cluster 1. And this is a rule for anomaly cluster 2. Type offers an option to the users to further refine the rules based on their needs. Notice in the last step, we have generated predicted points for each anomaly cluster. Now we can select the 2 points for each anomaly cluster that are close to their anomaly center. We then click the Generate Rules button again to update the rules. Notice that there's a slight change for rule for normal cases. We then check the rules for anomaly cluster 2. As we see, in the previous step, there are 2 rules listed for anomaly cluster 2. Now it's changed to 1. Thank you for attending my presentation. And now we are open for questions.
Thank you for the very interesting talk. So I check for the question. I don't see yet question. Please feel free to ask question in Discord or the YouTube channel. So I have one. What is the entry point of your system? So is it the scatter plot we see, and so the user spot an anomaly, so an outlier there, and decide that that's potential anomaly, and then all the rest unfold, or it starts from an automatic tool to detect the first anomalies?
Can you repeat the questions?
Yeah, so at the very first time, there is no anomaly, right?
Mm-hmm.
And so the user spot anomaly on the scatter plot, if I'm correct.
Yes.
Yes. So they are supposed to be isolated point on this scatter plot. And then you have all this system to expand kind of the anomalies and to categorize the different anomalies. So my question is, what is this scatter plot? Where it is computed? Is it a projection technique, like a PCA or?
Yeah, it's from like a multi-dimension scaling.
Okay, and so there might be distortion in such a projection technique. So you know that you may have potential anomalies that disappear because they are hidden in the middle of the core.
Yeah, you're right. Yeah, you're right. So this is why we pair that with other visualization, like isolation scores. So at the starting point, when users put their mouse on a single point, the isolation score will be fired. You can see on the like violin chart. So they can check both the scatter plot and the violin score to make sure like that point is exactly the anomaly point they're looking for. Also, if they have like some prior knowledge about the data set they are using, so they can go to the there's a barcode plot which directly can refer to like the distribution of the data by each attribute. So you can like they can check like the important attributes if they have some prior knowledge about that. Yeah. So it's not like just the scatter plot. It's there are other visualization that can combine with scatter plot. Yeah.
I see a question from Angelos. Is it possible to select more than one instances with the lasso selection, for instance? In the scatter plot, can you select more than one instance?
Yeah, of course. Yeah. So every time you can So like more than 1 points, but you have to click it one by one, of course.
Sure.
Yeah.
And is there any automatic technique to propose such anomalies instead of manually searching for them?
So right now we're like the visualizations are automatically generated. So so the users does not need to have like any human input when the algorithm runs at the back end. However, like we believe like user interaction, user input is a very valuable reference for generate anomalies, because anomalies are very specific to each data set. So so we want to like have some human input in that. So in terms of like automatically generation, that's something like I think he is quite interested, and we're hoping to expand our research to that in the future. Yeah.
Okay, I will read the last question. About the tool by Teng-Yok, can it show the original data item other than just the point? So I can imagine if you have image data, for instance, 1 point corresponds to 1 image. Are you able to see this sort of data in your tool?
Yeah, right now the data set we used are all tabular data, but like we are looking forward to expand that to other types of data, like texts or images or even audios, videos, right? Yeah, yeah.
Okay, great. Thank you very much for all your questions. We need to wrap up now. So thank you again to all the speakers, the audience, and all your questions, and the volunteers and the technicians too. Hope you'll enjoy the rest of the conference, and you can continue the discussion on Discord and Topia. Thank you.
Yeah, thank you.